Hey everyone, and welcome. I am absolutely thrilled to have you here today. In this explainer, we're going to unlock something incredibly powerful. We are going to learn how to literally read the secret language of industrial hardware. We're talking about programmable logic controllers, or PLCs for short. These are really the unsung heroes, the hidden computers that run the massive automated machines we rely on every single day. So just picture a high-speed bottling plant. You've got hundreds of bottles flying down a line every single minute. How does a massive, complex factory arm just know exactly when a single bottle has fallen over? And more importantly, how does it know exactly when to fire a pneumatic pole to push it off the belt without knocking over all the others? Well, it's not magic for sure. It's a PLC. The PLC acts as the hidden brain solving this real-world industrial problem using some surprisingly simple, elegant logic. And by the end of our time today, you are going to be able to read exactly how it does that. Okay, let's dive into this. If you're totally new to PLC hardware, don't sweat it. We're going to break this down step by step. Our agenda today covers 1. The brain of the factory. 2. Decoding inputs and outputs. 3. Logic gates, series and parallel. 4. Catching the pulse. And finally, 5. The power of latching circuits. Let's go! Starting with section 1, the brain of the factory. To understand these massive, kind of intimidating machines, we first need to figure out how they look at the physical world. Honestly, the absolute easiest way to think about a PLC is to treat it like the human body. The physical inputs, well, those are the machine's senses. This could be a sensor spotting a passing box, a thermometer feeling a sudden temperature spike, or just an operator pressing a start button. The PLC takes those senses, thinks about them, and then sends commands right to its muscles, which are the hardware outputs. We're talking about motors firing up, valves opening, or robotic arms swinging into action. It's literally just senses in, muscles out. Moving to section 2, decoding inputs and outputs. Now, how do we actually write all that down? If you've ever looked at a PLC logic diagram, it can look like a total bowl of alphabet soup. So here is your foundational cheat sheet. When you see the letter X, that represents an input. That's a physical switch or a sensor out there in the real world. When you see the letter Y, that is your output. That's the physical action happening, like our pushing pole firing or a light turning on. So X is the sense, Y is the muscle. And finally, M stands for internal relays. Think of M as the machine's short-term memory. It doesn't actually exist in the physical world, it's just a digital trigger the brain uses to keep track of things internally. Keep X, Y, and M in your mind, because they're the core building blocks for everything else we're going to talk about. Which brings us to section 3, logic gates, series and parallel. We've got our vocabulary, so let's look at the grammar. Before we check out our first diagram, we absolutely have to understand two fundamental states of being, normally open and normally closed. Think of a normally open contact like a raised drawbridge. Electricity simply cannot flow until something physical happens, like a button being pressed, which closes that bridge and lets the power through. A normally closed contact? Actually, it's the exact opposite. The bridge is already down and electricity flows freely right up until a sensor is triggered, which then breaks the connection. And this brilliantly illustrates the concept. Check out this series connection for our bottle sorting conveyor. The logic flows in a single, straight line from left to right. We've got two physical inputs, X0, which is a sensor at the very bottom of the conveyor belt, and X1, a sensor positioned higher up right at the bottleneck level. And way over at the end, Y0 is our pneumatic pushing pole. Notice the symbols here. X0 has a little gap, meaning it's normally open. X1 has a slash right through it, so it's normally closed. So, what does this all mean when a bottle goes by? In state A, a perfectly upstanding bottle passes. It hits both sensors, right? X0 detects the bottom and turns on, closing its bridge. Awesome. But X1 detects the neck and also turns on. Because X1 is a normally closed contact, turning it on actually breaks its bridge. The logic signal hits a wall at X1, so our pushing pole Y0 stays off. But look at state B. This is where it gets cool. A fallen bottle slides by. It hits the bottom sensor, so X0 turns on and closes the bridge. But because it's knocked over, it completely misses the top and neck sensor. So X1 stays off, which means its normally closed bridge stays connected. The signal flows all the way through, Y0 turns on, and wham, the pole pushes the fallen bottle right off the belt. It's flawless factory automation pulled off with just two sensors and one single line of logic. But hey, what if you want multiple ways to trigger the exact same muscle? That's where parallel connections come into play.
It's like a stairwell in your house. You've got a light, that's our output, Y1, and you want to be able to turn it on from the bottom of the stairs, X0, or from the top of the stairs, X1. By stacking these inputs in parallel pathways, just changing the state of either the top switch or the bottom switch completes the circuit and flips the light. It literally gives the logic multiple physical paths to reach the exact same destination.
All right, Section 4, Catching the Pulse. We've got the basic grammar down. Now let's talk about how a PLC processes time. Machines think incredibly fast, right? They process in fractions of a second, called scan cycles. Sometimes you just need a lightning-fast trigger. When you create what's called a rising edge pulse output, the split second you flip a switch, X0 goes from off to on, and that triggers a very special instruction called PLS, or pulse. Let's move through this and see how it builds chronologically. First off, your physical sense, the switch X0, turns on. Second, the PLC's brain executes that PLS instruction. Third, it generates M10. Remember our cheat sheet from earlier? M is an internal memory relay. So M10 fires off a pulse that lasts for exactly 1 microscopic scan cycle. We're talking a digital blip. But fourth, that tiny blip is all it takes to execute the set instruction on Y0, which physically turns on an indicator light. This setup lets the machine react to the exact moment an event happens, without needing someone to stand there and hold a button down. Finally, Section 5, the power of latching circuits. This is probably our most crucial concept today. Think about it. If that pulse we just talked about only lasts for a fraction of a second, how do we make the machine keep doing something? How do we give it long-term memory? We use latching circuits. Now, what's really wild here is that both of these setups accomplished the exact same thing in the real world, but they use totally different logic to get there. You've got a common latched circuit on one side and a set and reset circuit on the other. Both are basically designed so that when you press a start button, a light turns on and stays on, even after you pull your finger away. This right here is the true power of machine memory. By taking the output's own signal and looping it right back into the input logic, the circuit effectively holds itself on. It is latched. You tap X0 to start it. You release X0, and that Y0 indicator just happily stays glowing. The absolute only way to stop it is to press a completely different button, X1, which acts as a normally closed circuit breaker. You hit X1, the bridge drops, the loop breaks, and the machine shuts down. This simple, brilliant concept is literally how every continuous process in a factory operates safely, from mixing giant vats of chemicals to spinning massive motors. It's truly fascinating when you pull back the curtain, isn't it? We started with these intimidating, massive factory machines, and we've distilled them down to their elegant core. Senses turning into memory, driving physical muscles. By understanding just a few variables, X, Y, M, and the basic rules of how they connect, you now possess the foundational tools to actually read the hidden language of automated hardware. So now that you can decode these diagrams and see exactly how machines process the physical world, take a look at the environment around you. What complex real-world problem would you solve with a single string of logic? Thank you so much for joining me on this explainer. I really hope this sparked your curiosity, and I absolutely can't wait to dive into our next topic with you. See you next time.